Almost every game I've worked on has included some form of a pathfinding algorithm, the goal of which is to find a path between points A and B. Typically there's an additional requirement. Don't just find any path, find the shortest possible path. Meaning you're stuck with methods like breadth first search. Luckily, these methods are simple to understand. You start at the root and go to each possible location. From these, you explore the next set of possible locations. This exploration, one layer at a time, continues until the final path is found. This guarantees the shortest path because the approach is one layer at a time. But the problem is that you explore a lot of areas that aren't relevant. This is typically where people introduce the algorithm A* as an alternative to breadth first search. Because A* is faster in most cases, it still guarantees finding the shortest path. But A* is an extremely well covered algorithm, and I don't think I have anything to add to the topic. Instead, I've linked in the description 2 resources that I think stand out. The first is from a blog called Red Blob Games, and the post is titled Introduction to the A* Algorithm. It has a beautiful demonstration, and it even includes an implementation. The second resource on A* is a YouTube video from a creator with many videos on game development that I really enjoy. A*, though, doesn't solve everything. Pathfinding is an expensive operation. Whether it is in games where milliseconds count, or a maps application where any appearance of lag can frustrate the user, you want pathfinding to be as fast as possible. I currently have no inclination on how a faster pathfinding algorithm could be implemented, but that doesn't mean we can't make it easier for the already existing algorithms. Here we have a 50 by 50 maze. The code to make a maze like this is very simple if we're using Python. We're going to use NetworkX, which is a graphing library, and I have a link to their webpage in the description if you're curious. To make the maze, use NetworkX to generate a grid, and then use NetworkX's implementation of Kruskal's minimum spanning tree. A minimum spanning tree guarantees that there exists a path from one node to every other node in the graph. If we run A*, where we start at the top left and find a path to the bottom right of the maze, A* will take on average 0.77 seconds to find a solution. The problem only gets worse when the maze gets bigger. With a 250 by 250 maze, A* takes about 27 seconds to find a solution. Overall, this is pretty bad. I'll grant you that most games do not feature large mazes, and they include optimization so that the enemy will only be active when in the player's sight or within a certain range to avoid these kinds of problems. But still, we should be able to do better. The method I'm going to present is not a silver bullet, but it does strongly reduce the overall time to solve a maze. For example, a 250 by 250 maze is solved in 8 to 12 seconds, depending on the maze. So, let's talk about how we can get this speed boost. We simplify the graph, and by doing so we reduce the search space. Because the search space is reduced, there are less nodes and edges that A* has to work through to find the best path. Because there are less nodes and edges, the search is faster. Before describing how to simplify a graph, I want to point out that graph simplification is something that should be run offline, meaning before the application is used by a user. It is an operation that is not computationally cheap. It takes time to run. Also, I want to point out that this approach may or may not be original, but it probably is not. I'm not aware of any work that has done this, but I also haven't done a thorough review of the literature. With all that out of the way, let's discuss how to simplify a graph. The algorithm relies on this idea I'll call a critical node. A critical node is a node with more than 2 edges. This one isn't because it has only 1 edge. This one is not a critical node because it has 2 edges. This, though, is a critical node because it has 3 edges. A node with even more edges would also be a critical node. Now look at this graph and try to identify the critical nodes. Feel free to pause if you like. The first critical node is node C. The second is node G. The algorithm starts by finding each of these nodes. The algorithm then iterates through each critical node and follows the edges until another critical node is found, or there are no more possible edges. Let's say the algorithm starts with node C. There are 3 possible edges to nodes A, B, or D. Let's say we get node D first. When we follow the edges, we eventually get to the critical node G. In the middle are non-critical nodes. These can be collapsed into one node. We can do more though. Node A is non-critical, but it can't be collapsed further. The same is true for node B. On the right, we have a cycle between nodes G, H, and I. we simplify the non-critical nodes like we did before. Some of you may have concerns about directionality. For example, how do we know that node C will start with node D and G with F? Or, how does node G know that it can go to nodes H or I? This is solved with metadata, which can indicate directionality and cycles. The last problem is updating pathfinding to work with this new graph. Take for example the problem of finding the path from node B to node E. Node E is inside the node DEF, which I'm going to call def going forward. The way you can solve this is by using a node lookup dictionary. So, for example, if you input nodes D, E, or F, it would return the larger node def, which has taken their place in the simplified graph. Using this, A* will find a path from B to C to def. From there, we follow the nodes captured by def and replace def with D and E. Looking back at the maze example, here is the 50 by 50 maze you saw towards the beginning of this video. When we run simplification in A*, we get this. Visually, it's clear that the search space has been reduced. But by how much? The chart on the left shows the number of nodes for the normal graph versus the simplified graph. The chart on the right shows the number of edges for the normal graph versus the simplified graph. A surprising result is that increasing the grid size did not result in more or less compression of the graph. Instead, the reduction of nodes saw an average of 31.38% decrease for all grid sizes. The same was true for edges, with a 65.06% decrease of edges. There are likely improvements to further reduce the search space without losing pathing information, and that could be a cool area for future work. But again, you may find that someone has already figured this out in the literature. For those interested, all the code for this is available on GitHub, and I have a link to it in the description down below. I hope you all enjoyed this video, and have a great rest of your day.